Welcome back, everyone. Today I thought I'd share a little bit of how I like to play around with coding and modular arithmetic. I'm by no means an experienced programmer, so don't expect anything profound, but I've taken a little bit of Java and I enjoy how discrete math pairs so nicely with computer science. That's really just because computer science is math at its core. So that's pretty neat. I thought I'd first start by sharing this program that is the Euclidean algorithm. So it starts by having a method that introduces the idea to the user and then prompts them for two positive integers. It then returns those positive integers in an array and passes it to this method, which is called calculate GCD. So this is really where the Euclidean algorithm stuff happens. So this method just uses a while loop and has variables a, b, and r. So it sets r equal to a mod b and then updates the b and r to be then a and b. And so it continues doing this until it gets an r that's equal to 0. So until b completely divides a. And this is similar to the crux of the Euclidean algorithm of like that chain reaction. So showing you a little bit of how it works, looking at 24 and 16, it says greatest common divisor is 8, so that's easily checked. You can throw in some other random numbers that are rather confusing to find the greatest common divisor of, so that's really the power of computer science there. So this is what I wanted to show you guys next. It's a program that can solve linear Diophantine equations. So those again are equations of the form ax plus by equals c. And it's really based on the Euclidean algorithm, but has a little bit more complexity to it. So like the last one, it has this introductory method that introduces the program to the user and gets the a, b, and c. And then it passes those to this method, which is essentially the same as the method in the Euclidean algorithm, but as it goes through the cycle each time, it saves the remainder to this array list that I called rem. So there's also this method that checks to make sure there is a solution to the equation. So it checks to make sure that the greatest common divisor divides c, because if not, then there's no solution. And then finally, it can be passed to this method, which I will explain in more detail. So here we have, let's take the example of 251 and 37. These equations on the far left are all, they all come from the Euclidean algorithm. And then we can solve each of them for the number on the right-hand side, and that number is the remainder. So it is saved in the array list called rem, which also includes 251 and 37 at the beginning. So that series is essential to the workings of this method. So after we solve each equation for the remainder, then we have to write it in terms of 251 and 37. And we include at the beginning equations that make 251 and 37. So that's 1 times 251 plus 0 times 37, and then 0 times 251 plus 1 times 37. So for coming up with the coefficients for each equation, it's very much like systems of linear equations or matrix algebra, where you're adding and subtracting coefficients of rows. So we think this is actually easier to see if we look at it in the matrix form. So we're going to go ahead and do that, where you can see down below I have a column that is all the r's, so all the remainders, and then a column for the coefficients of 251 and a column for the coefficients of 37. And the question is, what is the coefficient of R3 such that R2 plus R3 equals R4? And so we use the series of remainders to find that coefficient. So for R2 and R3, the coefficient is -1 times R3. And that's how we get -1 and 7. For the next one, we have to ask the question, 29 plus what times 8 equals 5? And we can see that that would be -3. And so then the computer takes that coefficient and uses it to find the next row of coefficients for 251 and 37. And it continues doing this all the way down to the bottom of the matrix. So that's what this method does right here. And then it passes it to this other method that then extracts the coefficients of the second to last line to find the x and y that solve the equation of the greatest common divisor as c. So down here that would be -14 and 95. You guys can trust me on that, or you can check for yourselves. But that would be right here on this line with remainder 1, because the greatest common divisor between our a and b is 1. And so then it finds the multiple that c is of the greatest common divisor and multiplies that by x and y to get the solution to the equation. So that's pretty much how this works, and we can kind of see it in works now. So let's test our 251 and 37 first, just because we know the answer to that. And so we get -14 and 95, which is pretty cool. You guys can double check me if you're skeptical at all. So here's another one that you guys probably know the answer to, or at least like have a feel for. So 45 and 10. Greatest common divisor will be 5, so let's do some multiple of 5 for c. And we get out some nice giant numbers, which is pretty cool. Lastly, you can use this, like the Euclidean algorithm method, to solve any wild problems that you may be having in your life, ones that you have no idea how to solve. But anyway, so here we have those giant numbers. Turns out the greatest common divisor is 6, so that's kind of the error message that the program gives, is that 6 does not divide 284. So I tried it again with a multiple of 6, and it gave out those cool numbers. So yeah, you guys can play around with trying to code some of this stuff on your own, coming up with your own Euclidean algorithm method. I don't know, I think it's pretty fun. Let me know if you're interested in seeing more videos like this. I have some more kind of computer science math projects that I'm working on. So see you all next time.